Okay, so let's continue with finding the expected value of a normal distribution. So we have a random variable, x, that's normally distributed with a mean of mu and a variance of sigma squared. So you can just take that as is if you'd like, or you can work to find out why that is so, and that's what I'm doing here. So we're going to prove that mu is the mean and sigma squared is the standard deviation of this random variable x, and we want to use a moment generating function approach to get there. So with the moment generating function, we're going to get the expected value of this exponential function e raised to t times x. So like any expectation, whatever's within these brackets here or parentheses here will precede the probability distribution function. In this case, it's a probability density function because our random variable is continuous. If it was discrete, it would be a probability mass function. So in this case, the probability density function is 1 over square root of 2 pi sigma. Sigma is not under the radical, times e raised to minus x minus mu squared over 2 sigma squared. So this x minus mu over sigma, we'll see here, is a transformation that we're going to do in a moment. This transformation actually centers the variable z at 0. So we're going to create this transformation that this standard normal distribution has a mean of 0 and a standard deviation of 1. So to do this transformation, to create this z variable, it'll be whatever the value of x is minus the mu, which is the mean, divided by the standard deviation, which is sigma. And if we take the derivative with respect to x, it'll be 1 over sigma dx. And then to find x, because we're going to substitute this into our equation, right? So x is equal to z times sigma. If we just rearrange this or just solve for x, right, it'll be x equals z sigma, right, plus mu, and the derivative of x is actually, that you can derive it either way, but here it's just, you take, we want to solve for d, the change in x, right, dx. So multiply both sides by sigma, we get dx equals sigma dz. Now this is going to be important because when we plug it into the equation, so we had a sigma here in the denominator, the sigmas are going to cancel out, so we get this next expression, which is finding the expected value essentially of this z variable now, which is this new variable, which is the integral, and it's always from minus infinity to infinity of e raised to the t. Instead of x, we substitute in that z sigma plus mu, and since we got rid of that sigma, we just have z squared over 2 here. Okay, so let's work this out. So this is our exponential function, this is our power. So what we do is we do a little substitution, and we do a little multiplication here, expand this, and we have this additional term here, e to the z minus z squared over 2. So we're multiplying these two exponential functions here, and multiplying two of them, we add the powers together. And we can simplify this, so it's 1 over square root of 2 pi times this integral, e to the minus z squared over 2 plus tz sigma plus t mu. And what we'll do here is we'll remove the minus 1/2. So what we're trying to do is create this really, really nice expression that we can expand upon to return to this right here, right? So we get minus 1/2 times z squared. So you're pulling out this 1/2 from each of these elements here. Pulling out a 1/2 here from tz sigma, we have to multiply this by minus 2, right? Because if we think about it, it's minus 1/2 times minus 2 tz sigma will be plus tz sigma, what we have here. So to do the same in this term right here. So we end up having, now what we do is we end up just taking the first two terms together, because what we're going to do now is we're going to find these factors here, and then these factors will, if we expand them, will return us this this power here, but it'll give us an extra term. It'll give us an extra term. Not here, but it'll give us an extra term below. This et mu is a constant because we're not integrating, and this should be minus infinity to infinity. We're not integrating over t, we're doing it over z. So we can pull this out of the integral. So what we end up having is et mu divided by the square root of 2 pi times this integral. And we're taking this term out here, right? Now let's work on this a little bit. So we're finding kind of its factors, right? It's more than just that because there's a third term here when we factor this, but we're smart enough to realize that if we do z minus sigma t, right, and we factor this, we get z minus sigma t times z minus sigma t, right? And when we expand this, we'll get z squared minus 2tz sigma plus sigma squared t squared, right? So these first two terms here are the same terms that we have up here in the power of this exponential function. But then we have this nuisance term right here, right? Sigma squared t squared. So we're going to pull that out, but in pulling it out, we have to account for this minus 1/2. So by adding it here, right, as a positive rather than a negative, it'll cancel out the last term from this expansion. So what we have left over is the following. We get e to the t mu divided by square root of 2 pi. So this is a constant times this integral. And we have z minus this constant again. So this, basically, if we just forget about the e to the t mu, and just like move it out here and we just take it out. And we get 1 over square root of 2 pi times e to the minus 1/2 z minus this constant. Basically, we already know that this is going to be the probability density function for the normal distribution. Plus we have this other term here, right? So we can like make this a product of two integrals. This integral, and then I didn't draw out the second integral, but it would be a second integral over here. But this is also a constant, so we don't even have to care about it. It's a constant because there's no z involved here. So we can pull this out as well. So what we have left is e to the t mu times 1, because 1 over square root of 2 pi times this integral is basically the normal, which we did already in a different video. We were able to prove that this integral integrates to 1, right? So it's a PDF. So we know that this equals 1. So this first term is e to the t mu times 1. Well, this is also a constant. It has nothing to do with z. So we don't have to do anything. We just pull it out of the integral. So we get e to the t mu times 1 times e to the t sigma squared divided by 2, and that just equals e to the t mu times e to the t sigma squared t squared over 2. So this is the answer. This is the answer, right? The answer to our moment generating function. That's it. Now, what we want to do is we want to find the mean. The mean is going to be the first derivative at t equals 0. So we need to take the first derivative of this moment generating function, and that's going to be equal to e to the t mu time. Well, so here we have, because we're doing this with respect to t, right? So we have two exponential functions. So we're going to use the product rule for derivatives. So it'll be e to the t mu times the derivative of this term plus the derivative of e to the t mu times this exponential function, and that's what we get here. So we do e to the t mu times the derivative of e to the t squared sigma squared over 2, which is t sigma squared times e to the t squared sigma squared over 2, plus we have e to the t squared sigma squared over 2 times the derivative of this function, with respect to t, so you get mu times e to the t mu. Now, we set t equal to 0, because that's what we want to find. We want to find the first derivative with set at 0, with t equal to 0, and that'll give us the mu, it'll give us the expected value. So with t equal to 0, well, since this t right here is 0, this first expression is going to equal 0, and this t will be 0 here, so e to the 0 is equal to 1, and e to the 0 here again, because there's a t up here and as a power will equal to 1, so we just get mu. 0 plus mu is equal to mu. Bam, we scored. We're good. We're good to go. All right. So let's repeat it over here, right? We repeat it over here. I do a little rearranging. Well, to get, now what I want to do is get this. This should be the second derivative, not the first derivative, right? It should be the second. So we're trying to get the second derivative here. So this is a little bit more complicated. So this is just copying that first derivative of the moment generating function, and I rearranged it a little bit. I'm sorry for the mess here. I rearranged it. You have t sigma squared comes out here. We got e to the t mu times e to the t squared sigma squared over 2 plus, well, here I'm going to do the mu times e to the t squared sigma squared times t mu, and then I'll further simplify this. I'll add together these two powers, right, instead of just multiplying it. So I got e to the t. See, I did a lot of erasing. You know, that's just part of the deal. Again, if you know my channel and you know me, you know, it's been 40 years since I had to do calculus, and it's been a long time. So, but I'm a good student. So being a good student, you have to study constantly, and you want to keep on working and getting better. So that's a lot of erasing. Have a good eraser. So it's t mu plus, because these are two exponential functions, we can just add the two powers together. So e to the t mu plus t squared sigma squared over 2 plus, well, this is, we can just add these two powers together. We got mu times e to the t mu plus t squared sigma squared. Okay, so now we need to get the second derivative. So this should have a second derivative here. That's my fault. I didn't write that down. This should be the second derivative with respect to t. Well, so this is, again, we're going to use the power rule here. So we'll take the derivative of this first expression. So it's sigma squared, because this is with respect to t, so it's just sigma squared. And sigma squared is a constant. So it's sigma squared times e to the t mu plus t squared sigma squared over 2. So we got that part right here, right? Plus the derivative of this with respect to t, which is mu, right? So it's with respect to t times this first piece right here, this first little function right here. So you got t sigma squared times mu plus t, because the derivative of this little expression right here is sigma squared t, right? Because the 2's will cancel out when we take the derivative, times e to this expression right here. And then the second part here, just this itself, you just take its derivative with respect to t, so we get mu squared, because e to the t mu, this t, the derivative of this part of this sum will be mu, right? The first derivative will be mu. And then this will just be 2 sigma squared t, and then you have to multiply it by this exponential function, which we do right here. Then last thing we do is we take the second derivative and set t to 0. So when we set t to 0, well, this whole thing will become 0. E to the 0 is 1. 1 times sigma squared. This part here will just be 0 because you have a t down here, right? And this last part will get mu squared plus, well, this will be 0 because you have a t. So it's just mu squared. So you get sigma squared plus 0 plus mu squared. So that's the second derivative with t equals 0. Last thing we need to do is find the variance, and the variance is going to be the is the second derivative of the moment generating function minus the first derivative of the moment generating function set at 0 squared. Both of them are set at 0. T is equal to 0. This one is squared. This is equivalent to expected value of x squared minus expected value of x, the whole thing squared, if we didn't use the moment generating function. So we get sigma squared plus mu squared minus, well, we know that the mean is mu, or the first derivative of the moment generating function at 0, set at 0 is mu, so mu squared, right? So we get sigma squared plus mu squared minus mu squared, and we get sigma squared. That is so awesome. We did it. I love you all. We're awesome. Thank you, and have a wonderful evening.